Thank you, Pete. I can't say what a privilege it is to be here, to hear the white-haired architectural pioneers that brought us where we are and know where we're going, and to participate in the mealtime conversations with the next generation that will have to take us into this dangerous realm, and to see the great community formation that's taking place. You will be each other's peers as you wrestle with this new hardware on a series of problems that are largely common in infrastructure, even if they're very different applications that pay the bills. And this afternoon we begin a transition from the architecture to the algorithms and the programming models. And a narrative for this workshop, probably planned by Paul, but it seems sort of self-assembling to me, is that the architectural dark clouds, whoops, where did that, oh yeah, there they are, the architectural dark clouds of the end of the easy thousandfold every decade, and the end of bulk synchronous processing as we know it, for reasons that Pete and Pavana alluded to. We go from there to eventually to today's decent software infrastructure. Most of the rest of the week, MPI, PETSI, Trilinos, Hyper, sundials, and so forth, all the great infrastructure that many of you are probably familiar with and can use today. And the question is how to set out from today with a fairly usable infrastructure and programming models that we're rather fluent in, and port those with as much encapsulation as possible, as Pete has emphasized at every break, no matter what the architectural details are to come. So while I certainly don't have the final answers, I think I can indicate several good directions for setting out from today towards the exascale in algorithmic advances that will actually pay off already today with the sort of hybrid architectures we have on our desktops, and when multiplied by 1 million at the sort of infra exascale. So here's a challenge as we pass the baton. I always like to remember Ben Franklin's quote, walking out of the formation of the Constitution: a republic if you can keep it. So let's see if we can keep going, actually making scientific deliverables with the infrastructure that we have. So I'll put a conclusion up front that many of today's algorithms have a good hope to make the leap to greater concurrency, to less synchrony, even though they weren't designed that way and seem like they probably have way too many global reductions and other synchronizations, and even built-in resilience. A lot of algorithms that we don't give credit for having built-in resilience, like any of the subspace correction methods, like Gauss-Seidel or multigrid or whatever, if you keep A and B around, no matter what happens on the way of updating X, you can always recover from that. So many algorithms do have a built-in fault tolerance if we have a way of segregating our codes into parts that are guaranteed safe, like retrieving A from ECC memory and doing a lot of other things that are really cheap and fast and can conquer the power barrier. And that division of today's algorithms into those sort of robust and more fault-tolerant and energy-austere forms is your job. And the programming models will have to be severely stretched for this to happen, obviously. And everything should be on the table for trades that are over the thresholds. The astrophysicists really do need to talk to the NVIDIA and Intel and AMD people, and have to be willing. We may have to give up PDEs for lattice-Boltzmann or particle methods, or preconditioned Poisson solvers with fast multipole. There's a lot of things that may seem a little bit multidisciplinary, but those should all be on the table because we may need every single one of them. So the goal, really, I think I represent many of you in the room, is high performance with high productivity on all the multis, multi-scale, multiphysics in full dimensions, using probably multiple models, surrogates, as well as full, maybe multi-levels of refinement, do most of the work in the coarse grids in the low-dimensional subspaces to get a final answer that's accurate on the precision required, exploiting poly algorithms with different crossover points in multiple precisions, because half the precision is twice the memory bandwidth and twice the storage, in multi-protocol programming styles. We've already gotten into those. On multi-core, massively multiprocessor systems, and this requires you to be multidisciplinary. Of course, it's a lie. It's not really high productivity, but it's maybe the highest possible, and that's, I think, all we can hope for. And of course, we can't cover all the multis in this talk, but my simple point is, given the architectural stresses, how can new algorithms help? What directions can we set out today? So the purpose is to increase the quality, if you will, of the co-design dialogue between application user developers, like most of you, and the hardware and system software developers. And the vendors are surprisingly willing. I found even, holed up on an island in the Red Sea in the Middle East, Intel and NVIDIA have both, given us free, PHYs and Keplers, and are engaged in porting some unstructured PDE codes to those environments. So the vendors really are curious about early results and how it could influence their designs. Of course, there's no longer one type of vendor. It's already been alluded to. There's the vendors focusing on low power. Doesn't necessarily have to be reliable all the time. Smartphones, remote sensors. There's the high throughput vendors, and then there's the high reliability vendors for business and data centers. And scientists need all three, of course, but we don't deserve to ask for all three because we're a relatively small market. So we have to use these three specialized types of available commodity things to build a scientific supercomputer out of them somehow. A lot of the background of my talk from the algorithmic perspective comes from the exascale.org roadmap under IESP, put together over a period of about 4 years, the final document put together by our host, Pete Beckman, along with Jack, who you'll hear at the very end of the week. Many contributors, many agencies from the G8, and the goal of this multi-year workshop was to see how the software systems and applications would be able to ride the new hardware. It's clear that these 3 decades of factor of 1,000 every 10 years are probably over. We've had the same SPMD programming model, the same assumptions about who's responsible for what. The algorithmists squeeze out the flops, the vendors keep the floating point IEEE correct and give good global reductions for scalars that are very fast, and all these things that, it's been a good dialogue, a good system of, a good ecosystem today. And the same classes of algorithms have been successful. We don't just talk about LinPack getting better by a factor of 10, a factor of 1,000 every 10 years, but Gordon Bell on real apps has hugged that very same curve. If you look at, so it's less monotonic, but if you sort of draw a line through the peaks of the Gordon Bell prizes, they also are a factor of 1,000 every 10 years. But EXA is qualitatively different. You've heard that in greater detail than I need to do today. I'll only go over a few points in case the video has to be seen in a self-contained way, but I'll fast forward over the motivation and get to sort of the point that core numerical analysis and scientific computing will have to confront the exascale in order to maintain sponsor relevance. And this is not gray clouds. This is not a distraction. This is intellectually very stimulating. And there's potentially big gains in adapting to the new hardware environment. And this will be fun. These will be more fun PhD theses than blowing up stars or calculating evolutionary descent with bioinformatics or whatever. And the modelers are on the front line because without concurrent research beginning now, that's why Paul wanted to have this workshop, in the form of new models and mathematics, the passage to exascale hardware will lead little new scientific fruit. We'll still be using it more or less at the petascale. Scientists will find computational power to do things many have wanted, to go beyond just the forward problems, putting in the boundary conditions, the initial conditions, marching out the PDE. We'll put loops around that. We'll do inverse problems, we'll do control, we'll do data assimilation, so that the third and fourth paradigms, each of which has ugly errors, can make a beautiful child in predictive simulations, and uncertainty quantification. All these sort of headline goals for exascale will actually become possible. And scientists will participate in cross-disciplinary integration of these two paradigms. And also, even if you're not interested in extreme, remember that exascale at the lab means petascale on your desk with a system you can plug into the wall and actually compute with, if we get there. So we'll suggest some mathematical opportunities after very quickly reviewing the hardware challenges. And the first one, which I hardly need to talk about, is the relative cost in picojoules of doing a flop versus moving the operands that participate in that flop across the die. So, here is, I think, a number very similar to the one that you've heard this morning for the expectations of where we will be by about 2019 in terms of the cost of a double precision floating point multiply add, but lo and behold, it's an order of magnitude more to get those operands to the floating point processor. And this is a chart that I think has come from many people, but I think John Shelf is willing to stand by the predictions of, well, actually the assessments of today's average power costs per operation. And to echo something that Peter has made famous, a pico of anything done at an exa rate is a mega, right? So if you have, you know, if 100 picojoules for a flop today is done at an exa, that's 100 megawatts, and we've already been reminded a megawatt year is $1 million. And by the way, you use 1.4 kilowatts continuously, so this would be a 70,000 person displacement if we built a 100 megawatt computer. So that's a lot of people that we have to do better than. We've already heard from Trygve about Dennard and his famous paper about how logic scales k squared more power in terms of computational flops for constant electrical power, as long as the devices are all that you need. But if you have to actually move the operands through conductors, which wire lengths are getting narrower and so forth, that scaling doesn't work. The power for the communication actually goes up as you miniaturize. And finally, those curves, which were initially very far apart, are crossing, and we are no longer constrained by flops, but by data motion. Now, you heard Peter say that when they were predicting the petascale, they used every technology that was sort of in science fiction, and then when they got to the exascale, they said, well, let's use CMOS. Yeah, let's use CMOS, because you know, we have to bank on this thing within a decade. And in terms of software, it is going to be something called MPI plus X. I mean, there's just so much legacy code. MPI will have to be made much more robust and give us much more information so we can recover and be less synchronous and so forth, be variable in the number of things communicating. But we will be dealing with a distributed aspect in explicit messaging and a shared aspect with one of the many you know, already rather well explored hybrid channels. Now, of course, the current number one on the list, we heard it talked about. It's got 16,000 nodes, each of which has 2 Ivy bridges and 3 Xeon phi's. It's about 55 petaflops peak. It's front-ended by a machine with 59 teraflops. That's a pretty good front end. And this is a chart that I believe goes back to Pete, sort of containing one of the DOE exascale swim lanes, so to speak, what I like to refer to as a gigahertz kilocore mega node system, just to keep the prefixes easy. 10 to the 9 operation clocks per second on 1,000 cores per node and 1 million nodes, and that's this orange bar here. And these are the numbers in terms of gigabytes per node or petabytes per system. And we already heard about how memory austere Peter's system is. This one is much more generous, actually. The one that was in the IESP report. But this is the hard limit. And the Chinese machine is already up against the hard limit, not counting the cooling. It's actually twice over the hard limit, including the cooling. So this factor of performance that remains of some 20 has to be done, within the current power envelope. And so some exascale themes coming from those. Clock rates cease to increase. All the arithmetic capacity comes from concurrency, perhaps in core multiples as opposed to bigger cores. Storage capacity diverges exponentially below arithmetic capacity, so does bandwidth. Mean time between hardware interrupts shortens, and billions of dollars of scientific software won't really run right, or really won't run efficiently the way it's currently written. So what are the implications of operating on the edge like this? There's this draconian factor of power reduction per flop, at least a factor of 20, that will make copying less reliable, and even computing less reliable because of the voltage difference shrunk to near noise. And there'll be more errors that must be caught and corrected, either by the hardware or the system software, or by us. I claim we may want to do a lot of that. Power may be cycled on and off, and performance will be unreliable on a per core or per node basis, and that sinks all this bulk synchronous software that we have. It really wouldn't be hard to expand in a weak scaling way. The good algorithms we have today weak scale pretty well. They're optimal, and the computation is volume oriented and the communication is surface oriented, and Amdahl gets postponed and postponed and postponed, even though the log factor of the number of processors grows for global reductions. But if the nodes were performance reliable and we could load balance well, we could weak scale to exascale, the power we might not be able to pay for, but the programming model would work. But the real challenge is expanding the number of cores on a node up to around 1,000, what kind of cores they are. I mean, in some sense, the Titan is already more than 1,000 if you count each of the little CUDA cores as a core, but Peter discounted those. But this shared memory, strong scaling has to happen without much improvement in memory and memory bandwidth, and in fact, a degradation on a per core basis. And it's already orders of magnitude slower to retrieve an operand from DRAM, and it will get worse by another. So almost all operands have to come from registers or upper cache laid out by you, the combustion modeler, the astrophysicist, the subsurface modeler. So we're missing a lot of mathematics. New formulations are required with greater arithmetic intensity. That's flops per bytes moved in and out of these registers that are a cycle away. Reduced communication overall because of energy. Reduced synchronization because of performance unreliability. Assured accuracy with adaptively less floating point precision where possible in order to improve both memory and memory bandwidth. And algorithmic resilience to many types of faults. To do this, we'll need to quantify trades between limiting resources, and that recovers today's infrastructure if we can do that. Then we glue on all the other exciting things like PDE constrained optimization, data assimilation, and so forth. Arithmetic intensity, I think, has become quite a popular concept since Stan Williams' thesis at Berkeley a number of years ago. Here is an interpretation with respect to a number of algorithms or kernels that could be used to solve a Poisson-type problem, starting with the sparse matrix vector multiply that would be the inner loop of a conjugate gradient method. And if you think of X and B as being cache resident, and the matrix A as being used once, each element used once per matvec, an 8-byte word using in an addition and a multiply, that's a quarter of a flop per byte, just to drag A through, assuming everything else is perfectly mapped. In contrast, if you have a very high accurate fast multipole method, the data locality is such that you can get 2 orders of magnitude, almost 3 orders of magnitude more flops per byte. Now, what's the accuracy at the end of these factors? Actually, it's pretty good for fast multipole. That's another thing that has to be multiplied in here. But it's interesting to see this huge range of potential in the arithmetic intensity of algorithms doing exactly the same thing with FFTs somewhere in the middle. We recently have been exploring using FMM as a preconditioner in place of algebraic multigrid on simple Poisson-type problems, including some with variable coefficients. Here is a strong scaling on Stampede at Texas showing that fast multipole is initially some factor behind, but eventually it strong scales better. And this is all a sort of out-of-the-box synchronous version, nothing fancy. It can exploit asynchronousy perhaps better than AMG in the end. But there are crossover points, and we do need to think polyalgorithmically to take best advantage of hardware. Jim Demel and Jack will talk lots, I think, later in next week about AX equals B. So I won't say much here other than to point out that that kernel, especially for dense linear algebra, has been much explored with respect to reducing communication and synchronization because it's already the bottleneck to performance on today's hardware. Even within the sparse category, there have been many innovations like S-step Krylov methods. Where did I lose that? And block Krylov methods if you're presented with many independent right-hand sides initially, not always the case. Jim has this very nice tall, skinny QR which improves, which replaces a P with a log P in terms of the communication phases. Another possibility besides these classical methods is to invade the nested loops of the classical algorithms with operations dynamically scheduled with directed acyclic graphs in the data flow way. and to do some NUMA-aware work stealing to help load balance. We can also relax the domain of synchronization. We can't get rid of all synchronizations, but we can make many of the synchronizations over subsets of the global network. One example that does that is a nonlinear Schwartz, which replaces a Newton problem, where this is some large system of maybe a billion nonlinear equations and a billion unknowns with a Jacobian that you may not actually want to compute very often, but you can solve that problem in local clumps of nonlinear systems that either overlap or not, as long as every equation is included in one of those clumps. And most of the linear equation solving within the Newton method takes place within a much smaller domain. And there's still a global synchronization of a modified problem to get the answer in the original coordinates. How are most workhorse simulations implemented at today's infra-pettascale? They're mostly done, as was said earlier, with owner computes, iterative methods based on domain or particle distribution. Each individual owns a subset, does some concentrated work, and synchronizes and exchanges some important data globally. And this has many names, SPMD, BSP, CSP, and has been implemented successfully in many packages which encapsulate the communication and let you deal with mathematical objects like Hilbert space operators and vectors at a high level. But it's easy to weak scale this if you could be communication reliable. And this is an old argument. It basically has to do with volume to surface. And if you write sort of a complexity estimate for the computation, which is linear in the number of mesh points, maybe a lot of flops, maybe a few, depending on your physics at each point, the concurrent communication, the synchronization frequency, and a model of the architecture, which addresses how much the synchronization costs you. And then you can just do a simple calculus minimization. Let's ignore local communication and just take global arithmetic and global synchronization. And then you can quickly see that if you have a log-connected network, the optimal number of processors grows linearly in the problem size. And of course, there may be a convergence rate that degrades with the problem size. But if we have multigrid or something, that's a weak effect. And eventually, a log becomes large. But weak scaling works well if we can actually preserve good load-balanced synchrony. And this has been implemented in a number of ways, and you can study the weak points with some message passing diagnostics like the old jump shot or whatever, and see where communication and computation are imbalanced. Doing this at a billion threads requires much better software, but because you can't do it graphically. But the danger of non-performance reliable nodes is that one of these white spaces could just grow arbitrarily large and wipe out all the other things sitting there idling. And that's because we program in nested loops. This is our sort of core programming model. Here's the Newton-Krylov-Schwartz triple nested loop, which is concurrent over each subdomain on the inside, and that's where the thread is for imbalance. Why not roll back in computing a few decades to data flow models? Here is a famous problem for anybody doing energy levels in molecules or vibrational modes in structures. The generalized eigenproblem. There are 4 steps to get the eigenvectors and eigenvalues out of this, 3 of which are computationally intensive, numbers 1, 3, and 4 here. And these are the stages where the width shows the amount of concurrency available for a little 4x4 matrix, and the height shows the time. And if you do these stages sequentially, as you would if you called a conventional Linpack eigensolver today, you would have little concurrency and a lot of time. But if you put them into a directed acyclic graph, and Jack will show many other examples of this, I'm sure, in about a week, you can see how you get more concurrency exposed, and you can compress the overall time. This can lead to really great results on today's hardware with today's runtime systems like StarPU from INRIA, which builds a DAG dynamically and distributes it over heterogeneous hardware. And here is on 8 Intel Xeons and 2 Teslas. This is LAPAC, downloaded from the internet, and this is this star PU dynamically constructed DAG on exactly the same hardware, order of magnitude. Another idea is to do work stealing within a local memory basin. You don't want to spoil locality by moving things around too far. But again, and this is on an AMD Istanbul with 8 sockets, 6 cores per socket, using Barcelona's OMPSS. And here you see the peak for that hardware, the theoretical peak. Here you see DGEM, which is pretty much the operational peak, makes good use of the available bandwidth. Here's LAPAC. Here's a variety of other sort of adaptive architectural things. And here is work stealing within a local socket, not across sockets, but just sort of energy efficient work stealing. A lot of us want to do multiphysics. Multiphysics, the way we talk about it today, taking an ocean code and an atmosphere code and a ice code and honoring their interfaces and subcycling them while in between those communications and so forth, that probably will not be the way we do it at the exascale, because it leaves a lot of communication between those phases at the end of every major time step. So these green and these blue arrows, that's where the energy goes, right? You heard Peter Kogi talking about that. You can't have your 100 megawatt communication machine just to keep these little cheap orange arrows going. We'll have to have much better data locality than just gluing together the existing multiphysics codes. Many codes actually have algorithmic and software structure just like multiphysics. That extra physics might be the PDFs in uncertainty quantification. It might be the Lagrange multipliers in a constrained optimization problem. It's another working set of the same size as the forward model, and we go back and forth between them as if memory was flat. And this will, of course, have to end. Your generation will have to break the black boxes and figure out how to dynamically construct codes that have much better temporal and spatial locality. This is a slide I love from Bill Gropp, showing how you would not do a climate model, allocating different blocks of the world to different parts of the processor. Of course, for better data locality, you would divide them up like this. But if you were in a performance unreliable world with local work stealing, you might have to do something like this at any given time. And maybe he'll talk some about that as well. A number of us, sponsored by DOE, put some best practices of multiphysics simulations into a report which became a special issue of the International Journal for High Performance Computing Applications in January of this year. And I commend to you as a state of a snapshot of best practices, but probably not practices that will move to the exascale. An example of the problems of multiphysics is this CO2 sequestration model by one of my colleagues at KAUST. The CO2 in water is denser than the normal water, and it's subject to these gravitational fingering instabilities. The PDE model of the reservoir, Darcy's law, works very well in strong scaling on blue gene P, but the molecular dynamics model, done at every mesh point to get updated constitutive laws for these table points that are outside of the charts with very high pressure for the CO2 dissolved mixture, that tails out at about 128 nodes. That's actually due to three-dimensional FFTs. We hope to replace those with fast multipole and take that a little further. But these phases are way out of balance. This one's a couple orders of magnitude worse than that one. And this is representative of the problems of moving into multiscale. So I have sort of some bad news, good news, things to discuss. Each slide, I think, has some that we may consider bad news, but maybe there's a light in the cloud. We will have to explicitly control data motion. It carries the highest energy cost. We have to optimize that in the exascale environment. But we'll finally get the tools to do that. The vendors will have to give them to us, or the national labs will have to write them, or they'll be your PhD thesis if you're in computer science. We're used to controlling horizontal data motion under this 25-year piece of MPI that we've been experiencing, building great infrastructure, but we have not generally, other than maybe some prefetching or don't alias this kind of language constructs, been able to control the vertical replication of data into caches and registers. Now with GPUs, of course, we roll things in and out, and we're getting used to that. And we will enjoy scratch pads over caches because they will enable us to actually do exascale in under gigawatts. Another sort of pair of bad news, good news is that optimal formulations of today's algorithms may lead to poorly proportioned computations for exascale hardware, as we've heard about it this morning. Because all these methods were invented at a time when flops were expensive and memory bandwidth were cheap, and often memory was even flat. And that hasn't been true for a long time, but performance has been node reliable, and that's really the main thing that will probably break. So we may be lured by architecture into, first of all, formulations that are more arithmetically intensive, and that will help us to conserve what is expensive. And we will also be forced to abandon the global bulk synchronous paradigm, because it won't be possible for users to control the load balance sufficiently to make it work. There's too many knobs outside of our control. So the good news is that hardware and algorithmic non-uniformity will become, to some extent, indistinguishable at the performance level. When there's a time for a synchronization, our atmospheric model may have gotten out of balance. The sun is creating photochemistry on one side of the world, not on the other. Our mesh may needed to be refined. Those problems we're used to dealing with adaptively. But if the hardware is also getting out of performance balance, then we're going to have to actually build tools that will regularly and dynamically and preserving some measure of locality rebalance. And that will actually, besides being essential to live in the new hardware, it will free users to some extent from the very hard job. You look at the Gordon Bell Prize winners of the last decade, they rebalance almost every iteration because otherwise they just can't get those prize flops. Another pair of bad and good news is that fully deterministic algorithms may come to be regarded as too synchronization vulnerable. For example, rather than waiting for data, we may infer it. We may use machine learning to look at the last 50 arrivals of that message from that processor representing that unknown. We may Fourier analyze it and say, hey, I know what the next value is going to be. Let's move on. If it was wrong, we can roll back. But that's one of those optimizations that we'll always almost be willing to take. And there'll be a rich numerical analysis using a lot more tools from probability and machine learning and statistics of inferring missing quantities. And of course, robustly adjusting if we were wrong. But for performance, we may need to do that. Bad news, fully reliable executions. This is actually, fully reliable. The other one was fully deterministic. We may actually be partitioning our codes. This is a major programming model advance to take advantage of algorithmic-based fault tolerance, which will be much cheaper than checkpoint restart or paying several times the energy cost for ECC exchanges in memory or OS-mediated reliability or making sure messages get through, or whatever. Developers will partition their data and their program units into two sets. A small set that has to be done reliably, just like we would today, just like we would presume we could get today. For instance, to evaluate the latest residual, to check if mass is conserved, to do any number of things that help the user gain insight into the accuracy of the computation where it matters. And then a large amount of work can be done fast and without guarantees of reliability, knowing that errors can either be detected or, in some cases, you may have enough domain knowledge to know their effects are rigorously bounded. A spike in a diffusion equation, from one point with a bit flip in the exponent, it may instantly, in 3 dimensions, be gone in a couple of iterations. Examples of direct and iterative linear algebra abound. In fact, in 1956, von Neumann wrote a paper called The Synthesis. In fact, he gave 5 hours of lectures at Princeton on the synthesis of reliable organisms for unreliable components. I have an extremely hard time reading this paper, but the guy who invented digital computing and gave us our modern architecture provided for much less reliability than we have today. in his own mind. Bad news and good news with respect to precision. We are spoiled by default double precision. It helps us have really bad condition numbers for elliptic and biharmonic problems, and make the mesh a billion in each direction, and still have some digit or two in the answer. But it's wasteful of storage and bandwidth, and if we had more precisely tuned error analysis in our numerics, we could get by with less precision. We represent a smooth function with a cardinal basis. We store the full digits at each point rather than representing it in a hierarchical basis where the more detailed information takes fewer and fewer bits. I have a picture of that towards the end. We communicate full values instead of having maybe some hardware thing that's saying, last time you sent that message, all the bits were the same except for the last three, or why don't you compress that message? Flops are free, and decompress it at the other end. We can simply, sometimes predeterministically say, as in iterative correction in linear algebra, the factorization and the backsolve phase with the real A, those should be done in single. The residual computation can be done in double, and after a couple of those iterations, you can recover double precision accuracy. Classic algorithm that we don't really use anymore. So equidistributing errors among just the numerical part, or the numerical / hardware part, let alone all the uncertainty in the computation, the constitutive laws, the forcing, the initial conditions. That will be a lot of interesting numerical analysis theses. Just as a very trivial example of how single precision can be used in place of double in many cases, this is a brand new eigensolver by Nick Hyam called QDWH-EIG, and it's a method with fixed number of iterations based on machine epsilon. You divide the spectrum. It's a divide and conquer method, and you can prove it always converges in 6 steps for double precision. But based on the inner loops being successively rolled back to single, the first one, the second one, the third one, the fourth one, just do the last one in double, you can already save a simple factor of 20%. So how will PDE computations adapt? The programming model will still be some kind of message passing. That's the legacy code base. Weak scaling works. Adapted to the strong scaling within a node beneath a relaxed synchronization MPA-like interface that hopefully our colleagues from Argonne will tell us about for the rest of the next couple of days. Load balance blocks scheduled today with nested loop structures can be separated into critical and non-critical parts. And the critical parts will be scheduled with directed acyclic graphs. The non-critical parts can be made available for work stealing in economically sized aggregates. To take full advantage of asynchronous algorithms, we will need to develop greater expressiveness with this kind of partitioning into tasks which have different priorities, not unlike the way an operating system works today. And these priorities will be joined in a DAG, and there are already some experimental steps in this direction at Argonne, at IBM, and so forth. My favorite algorithm is Newton-Krylov-Schwarz, a nonlinearly implicit method for PDEs. The critical path on that is a linear solve to update the Newton step. You produce the Newton step with a linear solve, you bound it based on certain line search or trust region methods, and then you take the update. And it's really hard to avoid this sort of synchronous inner loop. But being lazy and writing procedural code with loops and subroutine calls, we stick a whole bunch of other things on this critical path that don't need to be there at all. We recompute the Jacobian, we refresh the preconditioner, we test convergence, we adapt parameters, we might do some I/O, we might do some visualization. These things can all be left as lower priority tasks to soak up the idle cycles that are presented by performance unreliable hardware and redeem a lot of that silicon and that power. There are many sources of non-uniformity. Some are already important. TLB mishes, can really torpedo, a synchronized computation. There's OS jitter. There's manufacturing variations. There'll be some new ones. The dynamic power management, more soft errors, more hard component failures where a node simply goes away, and the software that mediates resiliency will also be performance and reliable. So algorithmically, we're also used to these kind of non-uniformities, and this will, the solutions for the system will improve the programmability. Prior to possessing the exascale hardware that we may have by 2020, we can prepare by exploring new programming models on many core and heterogeneous nodes. Attention to locality and reuse is valuable at all scales of the computer. It will produce performance paybacks today because we are typically memory bandwidth limited already and often synchronization constrained. And the domains of coherence will have to become variable, perhaps adaptively variable, and hierarchical. New algorithms and data structures can be explored under the reliable assumption that flops are cheap and getting cheaper, and moving data is expensive and getting onerous. So the path for scaling up really has three factors that I think multiply pretty well. There's the weak scaling, which is proportional to the number of nodes if you can afford to replicate memory for each of those nodes. We may be at the end of that. It may top out at around 1 million and maybe 64 to 128 petabytes at an exascale machine. Within that, we have to strong scale to get the number of cores up. And then there's the workflow scaling. Maybe a lot of petaflops machines can run independent instances of ensembles that have only weak statistical synchronizations in an integrated end-to-end simulation. So the algorithm architecture co-design process can be staged with any of these contributions being valuable in and of themselves and probably multiplying fairly easily together. This is the software that we require to do scientific computing today. Some of it is model related, modeling the geometry, creating the mesh, choosing a discretization, partitioning, solving, adapting, perhaps generating random numbers, pseudo-randomly in parallel at large scale, doing various physics kinds of modeling, dynamic load balancing, graph algorithms. This is all stuff that is fairly close to the user. Then there's all the development-related software, the source-to-source translators to make us more hardware oblivious, compilers, debuggers, profilers. Then there's the production-related stuff to manage the workflow, to process the outputs, to design the inputs, and so forth. And all of that, is needed, but most of it doesn't come with the computer. Most of it comes from your PhD theses and the postdocs at the labs. And most of it is, in fact, contributed, sometimes after the fact. And I have my own tiny little niche, but I hope that all these other hard problems are sort of under surveillance right now. A philosophy which has stood the test of time in the infra-petascale has been what I like to call the SIDAC philosophy, where you have a large number of applications that at the level of the algorithms look very similar. They're PDEs on a mesh, they're particles in a globally interacting force field, they're agents, they may be graphs, but they present a relatively small number of formulations to the math community, which then presents a number of algorithms to the CS community, and of course there's a lot of over the border, over the threshold work there, but it's been very effective for DOE to force the physicists not to write their own algebraic multigrid, but to collaborate with people in OSCAR. And this model, I hope, will be one that persists as we keep going to rewrite all of this software down here. There is a working group in DOE called the Exascale Mathematics Working Group. Recently, the community was invited to submit white papers, limited to just 2 pages, on proposed projects that could be carried out in an exascale math campaign. And they're all available to you. And since these slides are available, you can look up this URL, hosted actually at Argonne. And they will be discussed in about a month in DC. These are just some of the examples of exciting algorithmic directions. Randomized algorithms, I'll say a word about what that means. On-the-fly data compression, mining massive data sets, algorithmic-based fault tolerance in many algorithmic areas, adaptive precision algorithms. If you have adaptive meshing, you have a reliable way of knowing where you have to refine. You check where some estimate of the error is too high. How will you know when you have gone too far with low precision? It's an interesting question to even develop the metrics on which you're enabled to adapt. And there's a lot of concurrency beyond the traditional one of space. There's maybe a little concurrency in time. There's a lot more concurrency in phase space, energy groups, angles, velocity space in both methods. And of course, there's increasingly a parallelism in the stochastic parameter dimension in uncertainty quantification. So there's a lot of really ripe problems to soak up new levels of concurrency, some of which may have good memory locality, some maybe not. All has to be studied. Just as an example of randomized algorithms, this is an incredibly encouraging result from Michael Griebel in Bonn. I think this was, this paper was 2011. There are basically three results here. This is solving a Poisson problem by pointwise relaxation, which, as I mentioned earlier, happens to be a very fault-tolerant algorithm, although this is all reliable computation. Here's the residual decreasing, exponentially with iterations, and here's Gauss-Seidel, which has a predetermined order to visit every point. There was a popularization of Gauss-Seidel in the pre-digital era when Alan Southwell was solving Poisson equations by hand in England, and he said, let me relax the points not in an IJK loop, but let me find the biggest residual and relax there first. And so the human eye could pick out, where's the big residual, and that very, highly steered computation is a Gauss-Seidel Southwell, which is here. That's very inefficient on a computer because you have to do a search to find the maximum residual. It's much cheaper to update all the points than to find the max residual. But what happens if you pick out 20 points at random and then find the max within that loop? You actually do as well as almost as well as finding the maximum residual, but you've only looked over a randomly selected group of points, which don't even really have to be synchronized with each other. In fact, these residual relaxations can be done totally independently. Just use the best available data from your neighbor, whether it's in the process of being updated or not. So a traditional highly regimented and slowly converging method, like a Gauss-Seidel, has, with almost no programming effort at all, and good robustness with respect to synchronization, a very a much better implementation. We mentioned a little bit about hierarchical representations. This is another little goodie to throw in before the questions. We talked about saving huge data sets. If we save the cardinal value of every field at every point, that is a huge data set. But if we use a little bit of math and find a better basis with which to reinterpret the smaller number of bits that we store, we can get the same quality of reputation, and this can be done on the fly. And the algorithmic idea goes back to sparse grids, which were invented about 20 years ago, where you instead of having a dense mesh with the fineness of these points in the bisectors here, you can have a coarse element representing just the middle point, and then two fine elements in each of the x and y degrees, and then these and in these skinny ones. And if you add up all these points and leave out the doubly finely refined, you get this kind of thing, which in 2D is called a sparse grid. If you do Poisson's equation on this, the complexity of, well, even if you just look at representing any function in this basis, never mind how you find the amplitudes, the complexity would be order n to the d in d dimensions. But the sparse grid actually has storage complexity n times log n to the d minus 1. We should be happy every time we can replace n by log n, Trygve told us right before lunch. So we should be happy to the d to the minus 1 times here, substantially shrinking the volume. And what do we pay in terms of accuracy if you want to evaluate the function anywhere in this domain based on this subset points? The n to the minus p accuracy, where p is the order of the basis functions, gets sort of degraded by a log n to the k factor, where k depends on p and d. So it's not a miracle. You throw away most of the data, you lose a little bit of accuracy, but it's a good trade from both ends, and very significant compression purely from existing mathematics. And you can see easily how it works. Here's a smooth function, a parabola, and just the first basis function gives you almost everything. But if you want to get a little bit better, you can add in the next 2. And eventually, by the time you get down just a few powers of 2, the amplitudes are extremely small. They can be stored in fewer bits or just ignored. You don't even have to store the integers, to find them. And this is an example for a 2-dimensional Gaussian, where this is a logarithmic scale of the amplitudes of the coarse mode going down to the finest mode in both directions. On a 3D mesh, for instance, it looks like that. And you can see that almost all the value of representing the function comes from a lower dimensional thing. This, of course, is a smooth function. It doesn't work for everything. But these are the kind of things that we would ordinarily just store lots of bytes per mesh location. And these are some of the things that we can start to do. So as we pursue the exascale, we do have a good petaops machine between our ears. It's about a petaops according to some neuroscientists. Pretty slow, but there's a lot of neurons, whatever they are, in terms of processing. But the amazing thing is it only takes 20 watts, not 20 megawatts. And so I hope we can use it to get somewhere. So the algorithmic part of this talk, basically summarizing a lot of the ideas from the original 100-page IESP, I put into a paper in Compte Rendu 2 Januaries ago. And I thank you for your attention.
All right, we have some time for questions. If you could repeat the question.
Yes, okay. I compressed the architecture part of the talk too much. Yeah, it's a brave new world. The Nuclear Regulatory Commission won't probably certify, any of these codes, or they're financial operations, Black-Scholes. There are a number of things where things are hugely at stake, where we actually do believe in the model, or at least we have a certified representation of the model that has to be done right. How common is that in astrophysics? Where the initial condition or some constitutive parameter may be not known within a factor of 10. How common is it under the Earth, where in our data-rich world we have very few mesh points? So there are a number of fields where already a fully deterministic simulation really should be given less credit and regarded as sort of an input-to-output map with some prior statistical distribution. And this is sort of the premise behind uncertainty quantification, which is one of the main customers for the exascale, if you look at Department of Energy strategic planning. And I don't mean to be irreverent about the importance of reliable computing, but when we compare all these other things that go into the input to output map in the scientific decision that needs to be made, should we support this treaty? Should we, not have to test this warhead? All these kind of decisions that come down to binary interpretation of lots of statistical data. Within all the simulations that go into that, it may be possible to discriminate against the outliers that are obviously hardware wrong, or just have them survive the UQ process if we have good enough statistics. If there's a systematic error, we may blow up the world. So yes, unit testing and all these kind of things become very much more complicated. I'm not an advocate of statistical means in computing. I have no resume there. I'm just trying to assemble some of the arguments from the exascale working group. I've read all of these white papers that are coming up next month, and my job here is simply to disseminate a lot of these ideas to give you some hope relative to the architectural doomsday stories that we've been hearing this morning. So your point is extremely well taken, and with these new less reliable tools, we'll need a lot more testing. We'll all have to become statisticians and and much more. But at least we can see how to get to the exascale in a useful way, I think. Yeah. So the question, to repeat, is about useful precision in a double precision multiply, and the fact that potentially up to half of the bits are discarded after the multiply. And could we use an instruction that just saved, spared that energy? I guess you couldn't spare the bandwidth if you want to initially presume that you have full. And this is just another possible tool to put into the hands of numerical analysts. We know that on GPUs, Double is much more than twice as expensive as single in terms of flops performance. That's probably because of the way that the chips were initially designed just for graphics. They're okay for FFTs, but for Krylov methods, we like to keep that extra 32 bits. It's definitely a hardware instruction that would be interesting for serious numerical analysts to play with. I'm anxious. I haven't really studied what's coming in MPI 3, but there will be a much bigger collection of operations that are less synchronous and more robust with respect to processes disappearing. And probably the first steps in harnessing the wonderful heritage of solvers that we have today will be to see where we can recover. Sometimes using mathematical analysis. If you're missing a piece of a PDE solution, it may be relatively easy using domain knowledge to make do without it. If you're doing a direct solve in linear algebra and you miss an element, a pivot or some row multiplier, you get completely the wrong answer. That one doesn't have the same robustness. Yes, you can detect it, by doing, X transpose AY and seeing if that's equal to, or Y transpose AX and seeing if that's equal to Y transpose B. There are various ways of checking things at every step even. I think each algorithm has to be considered, in its own right. One nice thing about one sort of point of light in Krylov methods is there's this preconditioning variable version of GMRes called FGMRes, which actually builds two Krylov spaces. One of them from which you pull the answer, and the other one which sort of gives you the coefficients for it. And using FGMRes allows you to vary the preconditioner at every stage, so you can use a Krylov within a Krylov, which is often a good, robust algorithm. Well, having a variable preconditioner is like having an unreliable preconditioner. So there's another place where there's already some fault tolerance built in that we don't necessarily think of that way. So I think there's a lot of sort of hidden nuggets of ways of repairing the current code base, but it will take a lot of thinking and some hard error analysis and some ultimately performance analysis in practice. How often do these cases come up and how bad are they?